The structure and operation of a Stirling engine. The Stirling engine primarily consists of two cylinders, one that is permanently heated and another that is permanently cooled. The cooled cylinder does not necessarily require active cooling. It can simply be exposed to the surrounding environment, ideally matching the ambient temperature. Only the heated cylinder is actively warmed by a heat source, such as solar radiation or waste heat from a technical system. However, actively cooling the cold cylinder with water can significantly enhance the engine's efficiency. In a Stirling engine of the so-called alpha type, the two cylinders are arranged at a right angle to each other, with their axes intersecting at the crankshaft axis. The cylinders are connected by a component known as a regenerator. Through this connecting pipe, the working gas is pushed back and forth between the cylinders. Unlike an internal combustion engine, a Stirling engine works without an explosive gas mixture. Hydrogen, helium, or just plain air can be used as the working gas. The Stirling engine is therefore also known as a hot air engine. It is a closed system with no gas exchange and no internal combustion. Like all heat engines, the Stirling engine also converts heat into work. As in combustion engines, this takes place by expanding and compressing the working gas, driven by a heat supply. Let us take a closer look at the thermodynamic processes inside the engine. In the 45 degrees position of the crankshaft shown, the gas volume is at its smallest and the gas is therefore compressed to its maximum. The total gas volume is made up of the volume of the heated cylinder, the cooled cylinder, and the volume of the regenerator. The respective proportions of the total gas volume are shown in the diagram. When the crankshaft moves half a revolution further, the total gas volume is at its maximum. The gas is then compressed again during the next half turn of the crankshaft. The typical phases of expansion and compression therefore occur during one revolution of the crankshaft. However, for the engine to provide useful work, more work must be done during expansion than during compression. To achieve this, the pressure on the pistons during expansion must be greater than the pressure during compression. Pressure is mainly determined by temperature. The higher the temperature of a gas in a closed system, the higher the pressure. When the gas expands, therefore, there must be more heated gas mass overall to exert greater pressure on the pistons. During compression, on the other hand, there must be more cooled gas mass in the cylinders so that the pressure on the pistons is lower. This is achieved by offsetting the cylinders by 90 degrees. Let's compare the two cylinder volumes during the first half revolution of the crankshaft. During this phase, the volume of the heated cylinder increases much faster than the volume of the cooled cylinder. Consequently, there is more gas mass in the heated cylinder than in the cooled cylinder. The pressure is also relatively high during this expansion process due to the relatively large proportion of heated gas. The expansion work done by the gas is correspondingly high. During the next half turn of the crankshaft, expansion is reversed to compression and the opposite effect occurs. The volume of the heated cylinder now decreases faster than the volume of the cooled cylinder. As a result, there is more gas mass in the cooled cylinder than in the heated cylinder. The pressure during this compression process is therefore relatively low due to the relatively large proportion of cooled gas. The compression work done on the gas is correspondingly low. The offset and permanently heated or cooled cylinders ensure that the work done by expansion is greater than the work done by compression. This means that useful work can be effectively gained from the process. The useful work comes from the heat input of the heated cylinder, which transfers heat to the expanding gas, thus ensuring an increased temperature. Note that the temperature of a gas normally falls as it expands. The cylinder must therefore be heated to keep the temperature elevated. Not all of the heat supplied to the engine can be converted into useful work. During compression, some of the heat energy is removed from the gas by the cooled cylinder to lower its pressure. The useful work is the difference between the heat added in the heated cylinder and the heat removed in the cooled cylinder. In the volume pressure diagram, this useful work is represented by the area enclosed within the cycle. Let's briefly examine the advantages and disadvantages of Stirling engines. The operation of a Stirling engine relies solely on the temperature difference between the heated and cooled cylinders. Depending on its design, a Stirling engine can function with extremely small temperature differences, even less than 1 degree Celsius. Some models are so compact that they can be powered by the heat of a hand. Another advantage of the Stirling engine is its closed gas cycle. Unlike internal combustion engines, there are no moving valves because there is no need to exchange the working gas. This eliminates the need for a gas exchange process, which in a four-stroke engine would involve idling. As a result, there is no requirement for a fresh air supply, which is necessary for combustion in petrol or diesel engines. This also means that no environmentally harmful exhaust gases are produced. In addition, there are no explosions in the cylinders of Stirling engines, unlike combustion engines. As a result, Stirling engines are very quiet and are often used in applications like submarines. They are also employed in combined heat and power plants. Another advantage of Stirling engines is their longevity, thanks to the absence of valves and the simplified control system. However, the advantages are also accompanied by some disadvantages. For instance, the power output of a Stirling engine is relatively low compared to a conventional internal combustion engine of the same size. Therefore, for the same power, Stirling engines are larger and heavier. This is referred to as having a high weight-to-power ratio. Another disadvantage is the control of the Stirling engine. While in internal combustion engines, power can be directly controlled by adjusting the amount of fuel and air supplied. In Stirling engines, this control is more complex and must be achieved through gears or changes in operating pressures. Let's take a closer look at the Stirling engine, and in particular the function of the regenerator that connects the two cylinders. Its role goes beyond simply transferring the working gas from the heated cylinder to the cooled one and vice versa. This connecting tube contains a heat accumulator, functioning as a heat storage, which is why it's called a regenerator. It is made of a gas-permeable material with the highest possible heat capacity, which can significantly improve the efficiency of the Stirling engine. In this way, heat is removed from the gas while it flows from the hot cylinder to the cool one, resulting in enhanced cooling. As a result, compression can occur at a significantly lower pressure compared to a process without a regenerator. Consequently, the work required for compression is reduced. The opposite effect occurs when the cool gas flows back into the heated cylinder during expansion. Ideally, the gas absorbs the heat that was previously transferred to the regenerator, resulting in a higher temperature compared to the process without a regenerator. This leads to an increased expansion pressure, and thus, the expansion work is greater. Overall, with the regenerator acting as a heat storage, this results in increased useful work and a higher efficiency. In the next video, we will take a closer look at the thermodynamic processes of the Stirling engine using an idealized Stirling cycle. I hope you enjoyed the video and found it helpful. Thanks for watching.